today. This is a inequality that looks pretty challenging, and I actually use two different approaches. I use the arithmetic mean in the Muirhead inequality. The Muirhead inequality was the bulk of the proof. The arithmetic mean ended up being, pretty straightforward. Now, let's go ahead and dive into this. We're trying to establish that this product right here, a plus b times b plus c, c plus d times d plus a, is greater than or equal to 16 times the product of a, b, c, and d. Now, I saw no way to do this other than expand it out, and this part right here was tedious. I didn't show all the work when I expanded it out, but you can kind of look at this and see that there's going to be 2 to the 4th, 6. There's 2, 2, 2, 2, and then technically you would get 16 distinct terms. But notice that we get 2 A, B, C, D here because they're kind of the front end and the back end. You see you have A, B, C, D that have to happen right here. Then going backwards, you have A, D, C, B. So you actually have 15 terms here, the 2 A, B, C, D happens twice. Now, Muirhead's looks kind of intimidating, but I'm going to show you what the approach here that makes it a lot easier than it looks. Like so many general proofs, if you first look at them, you go, God, how do you do this, But once you see one concrete example, all this notation makes quite a bit of sense, actually. Notice that a typical term here, like I'll just do this one, would have a sequence. You could think of this as 2, 1, 1, 0 as a sequence of exponents. Okay. So 2, 1, 1, 0 would be now there's some other ones here that we can handle, but we don't have to worry about them now. But all of these terms outside of a squared, c squared, and b squared, d squared have this exponent character to them. For example, this guy right here, this would be a squared, c to the first power, d to the first power. And notice that b is not present here. That's because it would be lined up with b raised to the 0 power. Okay. And so every single one of these is in this form. Now notice the order is not important because even though you have, d squared sitting here, you could rewrite it with d squared out front, right? But this b to the 0 certainly is equal to 1, right? And that means that b is going to disappear in this term. You just have a, c, and d. And the same kind of thing is going on. And so when you look at it like that, they all just lump into this category more or less, all right? Now, if you look right here, this would be in the form a to the first power, b to the first power, c to the first power, and d to the first power, right? And so what you get what they call a majorizing sequence, and let me write it down. We write down that, see, doing all this now, we can kind of go through it faster when we get into the actual proof. 2, 1, 0, 2, 1, 1, 0 is said to majorize 1, 1, 1, 1. Let me just write it down. Okay, so this sequence of exponents, that's what I like to call it. It's just but the symbol that they use is this crazy looking curved greater than. This is really just a greater than symbol curved because it's a different kind of greater than. But this sequence right here is greater than, in some sense of the word, 1, 1, 1, 1, 1, like that, right? Now it's greater in the sense described right here. Notice you have to have equality when you add them all up. When you add them all up, you get 2 plus 1 plus 1 plus 0 is equal to 1 plus 1 plus 1. This is what we're doing, is going through what constitutes a majorizing sequence, I guess you can call it that. But all this just equals 4, right? Both sides are equal to 4. So this is this condition right here, ladies and gentlemen, this is part of what it means for a sequence to be majorizing. Now, the next part, like we're definitely dealing with the case n equals to 4 here, right? N equals 4 is the case that we're dealing with here because we have 4 variables. So if we went down to k equals 3, that would correspond to this. In other words, and I won't go through all of them. Now you see you have a greater than or equal to situation, which is where this symbol comes from, kind of. So one of the cases would be 2 plus 1 plus 1. And this would be the k equals 3 k's, okay, is greater than or equal to, strictly greater than in this case. I'll go ahead and put greater than or equal to, but it does, that's what meets the condition. 1 plus 1 plus 1, right? Oops, 1 plus 1 plus 1. So right here we have certainly 4 is greater than or equal to 3. That would be for the case, we have to do k 1, 2 all the way up to 3. And I just did it for k equals 3. This is the k equals 3 case. Now it's not nearly as messy as it looks once you just see what's going on. You can kind of look at it and go, okay, I mean, this is bigger than this in some sense because you have the 2 up front, which always outweighs all these others. You know, they sum to the same thing, but this condition right here of successive inequalities is what makes this a majorizing sequence. Now I know that was time consuming, but I just wanted to make sure that's an important thing on the very next line. Okay, now just the very next page. Let me clear this out. Now, now folks, again, we are trying to prove this. And when you expand this out, notice you get this 2ABCD term. Now what we're going to do is just subtract this off, and this will become 14ABCD on the next page. It just ends up being slightly easier to work with. So again, this is going to become a 14 because this generates 2ABCD. All right. Now, okay, so let's run to the next page here. Okay. Now, what we're setting out to do right now, we're just going to show this based on what I just said previously. Okay. Now the rest of this is relatively fast. Okay, I just talked to you about the majorizing sequence. Well, because of this majorizing sequence, we're going to get this result right here. Now let me just back up. It's hard for me to keep this all on the same page, but this thing is true because of the fact that you notice this 2, 1, 1, 0, right? And then 1, 1, 1, 1. It's a direct correlation here between this majorizing sequence and what this inequality means. And this is what Muirhead says. This is a statement of Muirhead's. But let's just back up just briefly. See, that's what happens if you have two majorizing sequences. Ours right here would have been 2, 1, 1, 0 majorizes 1, 1, 1, 1. Okay. Now that means we have this inequality, which looks like a horrible mess, but we're only dealing with 4 variables. We're dealing with A, B, C, and D. Okay. This is written in a general form, so it looks intimidating, but it's really pretty easy actually. So let's go to this. So this is because of Muirhead's inequality. This majorizing thing implies this. Now, what does this SYM mean? It means you have to range through all the permutations of A, B, C, D. Now, I wrote those down here. This is tedious, but notice that there are 4 factorial, right? We have 4 symbols, A, B, C, D, right? So 4 factorial is the number of ways you can arrange n objects. In this case, n is 4. So we get 24, right? And y'all, there are exactly 24 permutations listed here. Look, 1, 2, 3, 4, 5, 6. Now again, now at this stage, this is tedious versus hard, right? But what I did here is I literally, and by the way, this piece right here is clearly going to be equal to when you're going to go through this 24 times, but it's just A, B, C, D arranged in the, a multiplication is commutative, right? So this is certainly 24 A, B, C, D right here. Right? We don't have to go through all of that. Now but this other one's a little harder, okay, because we actually have to run through all the permutations. And I did it by keeping the exponents fixed. I guess you could permute the exponents, but that's not technically what the theorem says, But anyway, there you go, folks. You went through, if you take a look here, A, B, C, D is this guy. A, B, D, C is this guy. You see how it's just 1 to 1. A, C, B, D is this one. Once you see the pattern, you don't really have to, it's not as bad as it looks. I would just characterize this as tedious. Notice our last permutation, DCBA, is what appears right here, DCBA, with the same exponent pattern. All right. Now, so anyway, this entire result, and I have to go to the next page, has to be greater than 24 A, B, C, D, right? This is the left-hand side, right? And by Muirhead's, this left-hand side is greater than or equal to this right-hand side, which is, we know it's 24 A, B, C, D, right? Okay, so let's run to the next page and complete this thing. Let me clear. All right, now, so all of that on the previous page was just equal to this, and sorry I didn't get it written down, but this object right here, okay, it's just hard to fit everything on the same page. This object right here, which we need to know, is just, they all happen in pairs. If you take a look, they all will happen in pairs. Let me just come back here. Just for example, notice that you have a squared BC happening right here. See, this is a squared BC happening right here, but you also see a squared BC happening right here. Right, again, y'all, a squared BC happening right here, and a squared BC happening right here. And they happen in pairs here, and there's 24 of them, so you got 2 times 12, the pairs, okay? So that's why I wrote this as 2, okay? So what we know, this entire piece right here by Muirhead's gives us this, but we can conclude that all of these guys right here in that same exponent pattern are greater than or equal to. You see how you divide through by 2? 24 divided by 2 is certainly 12, all right? Now, the other 2 terms, remember, this was our original expansion. The other 2 terms got resolved just by straightforward AM, GM. This is the arithmetic mean, geometric mean right here. This piece right here is just the AM, GM inequality. Okay, AM, arithmetic mean. So you see, we had to actually meld together 2 things. Just one little special case of AM, GM. Again, folks, that's these 2 terms that were kind of outcast, right? They didn't follow the pattern. And so we had to establish this inequality independently. But what we do is if we add this inequality, which you can do, if you add this inequality to this inequality, you get what we were trying to prove, right? Here, this is 12, this is 2. 12 plus 2 is the 14 that you see right here, and the rest of it all holds. Yeah, that was tough, but I thought it was interesting. Muirhead's is very, very powerful. And a lot of this that I showed you was just, once you see it, you may not have to go to as much trouble, but I was trying to learn it too. So I hope it was illustrative, and I hope it helped you.